Hi, I'm Mr. V, and this lesson is 4.1 Angles and Steepness. If you look under the Google Classroom, it will say to go to the Desmos link, and our Desmos link is found under the stream here for this class. When you open the Desmos link, the first question is the title page, and this is not sure what this is. Illustrative Mathematics is the textbook that we're using. This is from Unit 4, which is Right Triangle Trigonometry, and the lesson is on angles and steepness. By the end of the lesson, you should be able to say, I can explain why knowing one acute angle in a right triangle determines the ratio of the side lengths. That's our objective. And this first activity was to write as many equations as you can relating triangle ABC, which is similar to triangle DEF. And I would like to do that with you on my whiteboard. The first thing we could do is we could write a triangle similarity statement. And there's a number of different ways of writing this. I could say triangle, this in a different color, triangle ABC is similar to triangle DEF. And I could have said triangle BCA is similar to triangle EFD, or triangle CBA is similar to triangle FED. A lot of different ways of writing this. What I want you to notice is that triangles are similar. This does not say angles are similar. Angles are not similar, or sides are not similar. The symbol that we use for similar is this tilde. We also have the angles, and the angles are congruent. So I have the angle A is congruent to angle, it matches up with angle D. So if the triangles are similar, the angles are congruent. Angle B is congruent to angle E, and angle C is congruent to angle F. So we notice that the angles are congruent. And the symbol for congruence is equal sign with a tilde above it, like this. Not to be confused with just the tilde, or a double tilde, which means approximately, or some other things. We could also have written a proportion. So I could have said AB is to DE as AC is to DF as CB is to FE. Here I'm comparing large triangle is to small, large is to small, large is to small. And what we'll notice here is that the sides are proportional. They're not congruent. If they're similar, they could be congruent, but they're not necessarily. But the sides are proportional. And that means that you could write a proportion, which is an equation of two ratios. So 3 different ways of writing this. Some people tried to tell me that this was at right angles, and we don't know that. Someone said that angle F was the same as angle E. We don't know that. In fact, it doesn't look that this side is the same as this. This does not look isosceles to me. What I would point out is that if you use lowercase letters, we're supposed to use capital block letters for points. And if I'm labeling the angles, I would label it like this. However, with sides, I'll take the side opposite the angle, and I'll use a lowercase letter. So this would be side A, side B, this would C. This would be D, opposite of angle E is E, and this is F. So I could have written my proportion. A is to D, as C is to F, as B is to E. I could have written like that. Or I could have flipped it and said small triangle is to large. E is to B, D is to F, and D is to A, and F is to C. And what is even more important is if I have this angle is congruent to this one, and this is a right triangle, if this were a right triangle, and this is what we're getting at today, these two triangles are similar by the angle-angle triangle similarity theorem, which means that their sides are proportional. So I have the opposite of this angle, and the adjacent is equal to the opposite of the adjacent. So I could have B is to C as E is to F. So for any particular angle, this ratio is always going to be the same. That's going to be key for what we'll be learning later on. Now, I divided students into groups. We went to Jamboard, and in the Jamboard, each student was, if there's 4 of you in a group, you each chose a different color, put your name on it, and wrote in that color. So if you were to write, say, in blue for this person, I'm solving for x, I would write the formula. I'm going to say a squared plus b squared is equal to c squared. I'm using the right triangle. Let's see, the Pythagorean theorem goes with right triangles, and all of these are right triangles. So I will substitute in values. The x is going to be my hypotenuse, which is the longest side. It's opposite the right angle. So the x is associated with the c. And I have 3 squared plus 5 squared is x squared. This is 9 plus 25, which is 34, is equal to x squared. So to find x, I'll take the square root of both sides. When you do this, you'll have a plus or minus, but we're all going to ignore the negative root. And this value is my exact answer. I like this. What I could have done was approximated this. I could have said it's approximately. Instead of saying equal, I could say approximately, which is 2 tildes. And this is, if you put it into a calculator, it's about 6. I think it's like 5.8 when you plug it into a calculator. If I were a different student, and all the students can be doing all of these problems, but if I tried this one, and again, I write my formula, you'll substitute the values and we'll solve FSS as a graphic organizer for how to organize your work. A squared plus b squared is equal to c squared. I think I'll use a different color. I'm going to use black because it's easier to see. If I were to substitute values, some people incorrectly said 4 squared plus 6 squared is equal to y squared. And that would be incorrect because the 6 is the hypotenuse. It's the longest side. So this has to be over here. It doesn't matter which side you choose for A or B, but it does matter which side you choose for C. It has to be the hypotenuse if we're using a squared plus b squared is c squared. Now I get y squared is equal to 16. Y squared plus 16 is equal to 36. So y squared is equal to 20. Now I'm going to change this over to my whiteboard. And if I do y squared is equal to 20, I could write this as y squared is equal to 2 times 2 times 5. And when I take the square root of both sides, again, we'll have a plus or minus, but we're going to ignore the negative root because we're dealing with a distance. 2 could simplify. The square root of 2 times 2 is just 2, and then you have the square root of 5. So this is my exact answer, and I like this. I also like the square root of 20. You could put that in there. And if you wanted to approximate this, you could plug this into your calculator, and you would get 4.5, I think. But the question comes in with this guy for z. In fact, the synthesis of this activity, is it possible to calculate z? We don't know what this is. The only thing that we're given is one side length and an angle. We know that we can use the Pythagorean theorem if I have 2 side lengths, whether it's the 2 legs and I'm looking for the hypotenuse, or the hypotenuse and one of the legs, I'm looking for one of the legs. But here, I'm given an angle and a side length. If we don't have enough information to find the exact length of z, does it matter? Could it be any length? If this is 50 degrees and this is 3? If we had a triangle with the same angles as this, so if I have these 3 angles have to add up to 180, this is 90 plus 50 plus 40, this is a 40-degree angle. These 2 angles have to add up to 90, 90 plus 90 is 180. So this is 40. If I had another triangle that was a 40, 50, and 90, do you think, and I knew the side lengths here and here, couldn't I use them to make a proportion? And that's going to be interesting for us to see. Let's see what else in this lesson. Here's a Geogebra activity. In this Geogebra activity, we're dealing with a ramp. This is a real-world application of this idea that we're trying to propagate here. We didn't always have this situation where you had to have ramps going into buildings. Maybe you've seen ramps going into buildings. And when they make the guidelines, they had to make it to where it would be safe. And so maybe I ask you the question, what do you think makes a safe ramp? What has to be true for it to be a safe ramp? What guidelines would you create if you were doing it? And here we said a school has 4 steps to the front door. So I'm going to make this 1, 2, 3, 4. And Each step is 7 inches tall, so you could tell me how long it's going to be is another thing you could do. But I'm going to try to see what makes this a safe ramp. Maybe it's like this. I see here I got 10, 20, 30, 40, 50, and 50, and this is 4 tall. And you can change this. You can move this over to where it snaps into one of the points, and I can make it exactly level here, trying to get it to be level. And you can also move it over to measure it. So if I'm looking at what is this, 50 to 4 or 4 to 50 ratio, what is my angle going to be? I could look here and I can zoom in and I can see what this angle is going to be. And it looks like it's going to be about 4 and 4.7, maybe 4.6, something like that. Not quite 5, not quite 4, and a little bit more than 4.5, but not much more than 4.5. And then we look down below at the ADA guidelines. ADA is the Americans with Disabilities Act. Ramp guidelines. Ramps are required to be, for any change more than a half an inch. Wow, that's tiny. Ramps have to have a maximum slope of 1 to 12, which is 4.8 degrees. How did they know that? Ramps have a minimum width of 36 inches. There must be a 5 foot by 5 foot flat area at the top and the bottom for turning, meaning for turning with the wheelchair. Ramps may be no longer than 30 feet long overall between the flat rest and the 2 platforms. So this has a maximum of 30 feet. And let's see what else is there going on with this question. So when you looked at this, you tried this out, will any ramp with an angle of 4.8 degrees have a slope of 1 to 12? Will any ramp with a slope ratio of 1 to 12 have an angle of 4.8 degrees? How do you think that the people who wrote the American with Disabilities Act found a ratio of vertical length to horizontal length that is true for every 4.8 degree angle? And in the cool down, you're going to see another example of this, so we'll talk about that in a moment. Does every angle in a right triangle give you a fixed ratio of vertical length to horizontal length? And so, for example, I could ask, if I have a right triangle like this, and I have an angle here. If this angle is 10 degrees or 20 or 30 or 40 or so forth, is this going to be a fixed ratio of, here I have the opposite side and the adjacent leg. So is this ratio of the opposite to the adjacent leg always going to be the same? We don't know what it is for these other degrees, but I do know that if I have a 4.8 degrees, then it's going to be a 1 to 12 ratio. That's the one thing that we learned from this lesson. It's always going to be 1. So if I have a rise of 1, this would be 12. If I have a rise of 2, this would be 24. If I have a rise of 3, this would be 36, and so forth. And so it's always going to be a 1 to 12 ratio for this angle to be 4.8 degrees. 36. So finally, let's see. There is a synthesis for you to read. And on this sidewalk ramp, here's the actual question. The curb is 4 inches tall. And you have to follow this 1 to 12 ratio. So how long does this ramp have to be? And if it's a 1 to 12, what you could set up is a 1 is to 12 as 4 inches is to x, and then solve for x in inches, not in feet. Flared sides, these flared sides here, have the same type of guideline as a 55.7 degrees or a 1 to 10 ratio. So if you have a rise of 4 inches, how long of a width did these flared sides have to be? So if it's a 1 to 10 ratio, and you're going to go for 4 inches tall, how wide does it have to be? And that's the lesson for today. Good luck and success.